How well did your design meet the specifications of the performance test?
So for our robot, our original design for the performance test was we had a wooden arm sticking off of here that was immobilized, so it just stayed here and it was just chilling. And then we had this arm, which is motorized by a servo motor made of aluminum that would move up and down. So for the wooden arm, we were going to have it go just enough into the little opening between the ticket order and the wall, and we would have it, and then it would turn at a high speed, and then back up, and then push it again at a lower speed, so it would stay at the end. And then for this arm, we had it hold the tray initially at an upper angle, and then when it went up the ramp and got next to the tray, we wanted it to just fall down and then it would slide in.
Did your design perform as you expected it to?
No, it didn't perform as we expected it to because it took us 5 tries to get all the points on the performance test. So one of our issues was with our arm that was sticking out. After it turned to slide the ticket all of the way, in our program we had it turn like a certain amount of inches. So during the performance test, the robot was turned, but it still hadn't turned the full distance that we told it to, so then it was just stuck in that spot. So that was one of the reasons why the test didn't work. And then also another thing that happened was just with like the rubber bands like on the wheels shifting, so it didn't go up straight on the ramp. And also the last thing was when we had our robot go back to touch the burger, in some tests we told it to go a far enough distance, but in one of the performance tests it just didn't reach the burger. So in the next try we had to change our code and make sure it went far enough for that. What are the strengths of the design? What elements should remain the same going into the next performance test or competition?
So the mechanism we have for dumping the tray worked really well. It didn't have any issues. It was able to slide off really easily, so we're going to keep that the same. And we're planning on using it for the burger flip and for the ice cream levers. So we're going to keep it exactly how it is and hope that it works in the future.
How can the design reasonably be improved for the next time your robot needs to perform these tasks?
So we had, it's gone now, we had a temporary arm on the front that was just sticking out that we would use to stick into the spot between the wall and the ticket and push it over. And so in the future we are doing a rack and pinion mechanism with a servo motor to slide out of the side of the robot and use that to move the ticket slider instead. This would be a better solution because it'll meet the specifications for the dimensions of where the robot has to be, because it'll be able to slide off of the robot and back on to stay compact.
What problems did your robot experience and what were the causes of these problems?
Some problems that our robot experienced was the sidearm and the motor drifting. The sidearm was originally did not have tape on it, so when we dropped the tray off, it would get stuck at the end. The ramp also posed a problem because when we were moving up, the motors would drift and make us have some variance of where we would drop the tray off. There was also problems with turning because we were having difficulty with approximating the turns. Sometimes the turn would be it would go over by a few degrees, and sometimes it wouldn't go enough. There were also problems with getting stuck on corners. This would make the turn not complete because the encoders weren't moving.
How will you address each of the problems to ensure success in the future?
So one of the problems we had with our ticket slider mechanism was that it just wasn't very consistent. So in the future, we're going to be working on a new mechanism, which will use a servo motor and then a rack and pinion, which will extend an arm, and then the robot will be able to put the arm in the gap and then drag backwards with it. We think that overall will be a more consistent way of completing the task. Another problem we had was with turning, like just with the wheels. We have a few ways that we're going to solve that. One way is we're going to glue down the rubber bands that we put on the wheels in order for it to get up the ramp. We think by gluing them down, they'll just stay in the same spot and there won't be inconsistencies when we're testing. Also, we're implementing PID into our code, which will just keep track of how many counts each of the encoders are counting. And then based on that, it will recalibrate how much power each motor should be getting as it drives. And also we're going to be using RPS for the first time, which we think will be really helpful, especially with like orienting the robot and being able to do nice like 90-degree turns and stuff like that. And finally, we're also going to recalibrate like the values that we got initially for how many inches it takes to do a 90-degree turn, because those values are a little outdated, and that's what we used for the first performance test. And since then, like the physical aspects of our robot have changed a lot, so they need to be recalibrated. So we think with all of those, testing will go more smoothly, and it'll just be easier for us to know which way our robot will be facing and make accurate turns with it. Oh no. Oh yeah. See, we made our wheels not straight on purpose, so it's able to correct itself for that. No, I'm kidding. Alright, so I added like 4 inches, so it might push a little more. Are we allowed to pick it up after?